started off just being interested in inflammation and what happens to white blood cells when they leave the blood and enter tissues in an inflammatory response. And what I wanted to know was how these cells got out of the inflammatory response so the inflammatory response could go away. And when I started, early in my training, when I began my post-doctoral fellowship, I thought it was possible that some of the cells that went into tissues might just head back to the bloodstream and then clear the tissue. So I set up ways to try to track the fate of those white blood cells. And I ended up not finding any going back into the blood, but I found lots of cells tracking to the lymph node. I viewed lymphatics as the highway, and that's it. So I would, look at the cells on one end, like a tissue like skin, and then move to the lymph node. So I was invited to the first lymphatic research conference. So this conference, 10 years ago when it started, the community was really small, so I don't think they were really interested in people who were interested in inflammation, but just to fill in the gaps of leukocyte trafficking. So I came to the meeting and I learned about all of these, really I learned about the vessels, and I found it so intriguing. It's just like when you think about something very simply and then you realize it's got all this structure underneath. So I really was excited. Went back to the lab and presented what we learned, and we started thinking more about the vessels. So as time passed, we kept studying how leukocytes or white blood cells traffic to lymph nodes. Lymph nodes are always surrounded by fat, even at birth. Mostly for immunologists, this is just something to ignore. We throw it away when we're harvesting the node. In fact, it's actually kind of a difficult tissue to deal with for some procedures, so we just basically dissect it off. And so while we were studying this trafficking to the node and trying to do the math of, okay, these guys left, they got there, we realized that we couldn't add everything up, that it seemed like cells were arriving to the lymph node that weren't really necessarily coming from the skin. So we had this idea that, well, maybe we shouldn't be throwing it away. Maybe cells are moving into the fat as an alternative to going to the lymph node, or who knows. But we decided that it would be a good project to try to ask what's going on. So what we ended up finding was we would put materials in the skin as if we were starting an immune response, so things that we could see that were fluorescent, and we found that they were leaking out into the fat that was surrounding lymph nodes. And so for immune cells that are now there, and so in this case it started off as proteins that we were tracking because we were interested in immune responses, and usually vaccines, for example, are proteins. So we would see that immune cells could take up all this material. But it became apparent that the fat cells that are around the lymphatic were able to respond to what's coming out. And it was really a surprise because around the time that we started to see this, or just prior to this time, everyone thought that part of the lymphatic vasculature that moves through fat was completely impermeable. Even water wouldn't move out. So we're still studying the fat around lymph nodes. What's really interesting about it is the fat around lymph nodes, say in the necks of humans, can have two different states. So it can be this brown fat that generates heat, or white fat. So one thing we're really interested in is that maybe the purpose of the state when it's generating heat is actually to provide like a local fever response, which is more limited. Fever presumably is beneficial to the immune response. But that kind of response never happens in other fat pads. So we started the Crohn's disease project because I showed these data that we had to clinicians who work on Crohn's, and they were like, well, but Crohn's is so interesting because there's this creeping fat phenomenon together with potentially altered lymphatics. It's not clear that all adipose tissues have the same, or fat tissues have the same lymphatic structure as developed as the mesentery around the intestine, but we have been able to find that all human fat tissues have lymphatics, which had actually just a few years ago was debated, believe it or not. That's really how little information there is. So our argument is that there is some leakage that's normal. And in fact, there's plenty of fat that's normal. Fat is important. It's important hormonally. It's important for being able to give birth. So maybe it's an untested. It's not a completely clear that the fat around lymphatics is driven by lymph leakage, but I think it's a very reasonable hypothesis to continue to try to test, and it fits with the concept, which there is a little experimental support for, that that when lymphatics are less functional than normal, there's even more leakage, and that could contribute to greater growth. One of the things that we think when we see these veins really not remaining very healthy is that probably perfusion of the fat is quite negatively affected. So absolutely, a whole, future, is waiting to sort of explore what's going on with the adipocytes. So we did notice, we found a couple of strains of mice where the leakage is very poor when we would put protein tracers up in the skin, and the fat cells were very, very different when we did electron microscopy. So their powerhouse, their metabolic powerhouse called the mitochondria, really, really, like there's either more mitochondria and the whole structure of the cell is altered. And how hormonal will influence that, I have no idea. But I mean, there's naturally different characteristics between even men and women. And so when you're working with mice, you have to pretty much choose, because you're going to get really, really different results that are probably driven in part by hormonal differences. We have, as humans, really kind of small lymph nodes, but lots of them. And proportionally, our lymph nodes are much smaller than a mouse. And so I'm always surprised when we're seeing lymph nodes in these samples. I'm like, that can't be it. That's ridiculously small, compared to what I envisioned it should be on scale. But what's very interesting is that, as he's saying, it would make so we have a lot in chains. So in a way, every one of them is potentially interrupting this requirement for pressure. So then it suddenly makes sense of why removal of a lymph node in breast cancer could lead to lymphedema, and then consequently fat buildup, if the fat buildup is related to leakage for vessels that aren't very functional. One of the things that we will attempt to answer over time in my laboratory is there a purpose to the fat around lymph nodes? And we decided to start with this heat-generating fat because it's a little easier actually to deal with heat than think about at this point in time. We would eventually like to track fatty acids, but we need to develop some traction in the field, a reputation in a way, and start to do those are more challenging, I think, things to tackle. So we're asking if, right now, in the metabolism world, it's thought that if you can turn fat that stores lipid to fat that generates heat, that would be really beneficial. So we're trying to ask if that's beneficial to the lymph node. But embedded in all that, we are also interested to ask what happens if lymph nodes don't have fat. Metabolism is a very big area. And so it would be nice for it to come into some, I think areas where it interfaces with vascular biology is still a frontier.